Hello students. In the previous interaction that we had, I've just given you a very high level overview of what the course would be about, without diving into much details. And following that, I've given you some insights into how the grading policy would be and uh, what would be the weekly activity with respect to the course. Now I'm going to start the very first module 0. Let's name that as introduction module. For the first few lectures, I'm going to discuss about what computer architecture is. Following that, we are going to dive into some of the technical aspects which will help us to measure the performance of any computing system. So to begin with, I picked some of the flow of this introduction from Professor Onur Mutlu's lectures because I found it very good and very intuitive to present a very holistic view of what computer architecture is. So to begin with, this is the question that we are trying to answer at this moment. What is computer architecture? So let's start with what's popularly called as computer system stack. I hope some of you have already seen this. Even those who haven't seen that yet, it's okay. As your computer systems related courses build up, you will get an entire overview of what the computer system stack is. Basically, it has many layers, starting from the physics on how a semiconductor works or any other type of material works. Following that, how we use those materials to build what we can call as transistors. If you go the level next to it, how we use these transistors to perform some logical action. For example, an AND operation or an OR operation or an XOR or a simple NOT, left shift, right shift, etc. Along with that, we also have an understanding of how these transistors are used to create some memory elements like the latches and flip-flops. Above that is the microarchitecture layer, wherein we are going to use these gates and registers and some logics like multiplexers, decoders, etc., to build a more bigger computing platform, for example, like a CPU. Now, what does the CPU do? What are its capabilities? What are its limitations? Uh, how do we talk to the CPU? All those will be given to us by what's called as instruction set architecture. Now, the ISA is kind of an abstraction between the hardware and the software layers. Also, we can say that ISA is kind of an agreement between the hardware and software, saying that the hardware will be built following this some particular ISA, like the ARM ISA or x86 ISA, etc. And the software will adhere to the same ISA and build its applications. Beyond the ISA layer, the very first software layer that we see is machine code, which is just a sequence of zeros and ones. Above that is an assembly language. Following that is a programming language, typically the high level languages that we see today, very predominant are C, C++, Python, Java, etc. And we use these programming languages to implement an algorithm. And why do we use an algorithm? Because we have an end application in mind. So if you start from the top, we have an application in mind. For that, we pick a appropriate algorithm, and to implement that algorithm, we pick an appropriate programming language that will be converted to the assembly language using a compiler That's what we do typically once we are done with verifying the correctness of the program, etc. We are going to compile it. That generates the assembly language of that program, and that assembly language or assembly code, uh, to be more specific, will be converted to the machine code by an assembler, and that machine code eventually runs on the hardware. So typical computer architecture focuses on these four layers: microarchitecture, instruction set architecture, machine code, and to some extent assembly language. This is you can consider as a narrow view of computer architecture, but a more holistic view is where it spans the entire computer system stack. It means that typically when we build a computer, we need to have an end application in mind. We need to specify or keep a set of applications in our purview so that the hardware we build will be useful to them. Okay. Now, if we come up with any idea that is spanning across multiple such layers, that would extract the best out of the hardware and the software. It's called hardware software co-design. If we simply focus on the hardware, maybe we have the best hardware, but we do not have a good enough software to utilize the maximum potential of this hardware. On the other hand, maybe we have the very good software, but we are trying to run it on a hardware which is very inefficient. Maybe it consumes a lot of time or a lot of power, or maybe it's very bulky, etc. Now, one very good uh, example would be your Apple products. For example, if you consider an Mac book or even an Apple iPhone, the way it is built is they start from the application and they build a tailor-made hardware for it. That is the reason you see that many people use the same iPhone for a lot of years, because it works. There is no blotting of the malware or anything like that. Not to degrade or belittle any other company, but properly, if you see, it is well known that some of the Samsung phones use up too much of the internal storage, that after a few years the entire system becomes very slow. To even unlock it takes a couple of seconds, because Samsung primarily uses a third party hardware, and they put their own software on it. They don't understand the complete design that underwent into the hardware, so that they can get the maximum out of it. So the particular aspect of hardware software co-design is really important for a long lasting products and quality products. Computer architecture, which primarily deals with the microarchitecture and instruction set architecture, spanning across few layers above and below them, is a very niche area. And like I mentioned, its view spans across multiple layers of this computer system stack. If you're unaware of this, just like we have many popular software development jobs, we have quite a few architecture jobs wherein we either work as performance engineers or hardware architects or performance architects that help us create better and better hardware for a set of applications, or it can be the other way around. We are refining the application so that it can use the hardware better. So I hope this course will give you some flavor of such aspects. And to get a complete view of this computer system stack, you would be undergoing a course in operating systems, and if you have compilers course, that also would help you. But what at least I would try to give you is a cross-layered approach. What basically computer architecture is, it's the science and art of designing computing platforms. Anything that performs some form of computation or another. It can be designing a better hardware, it can be designing a better interface, or designing a better system software, or in the end, even the programming model. Why do we design these, or why do we refine them? Is to achieve some set of design goals. For example, it can be that we want to build a hardware, we want to build a chip that gives us highest performance for some particular workloads, namely X, Y, or Z. This can be one design goal. Or our design goal can be that my hardware should run on minimum amount of power supply so that, or consume minimum amount of power so that the battery that comes with it can last longer. So one very popular notion that we have is all day computing. It means that when they build the laptop or a tablet, or many a times some high-end mobile phones, they say that you can perform some intensive work on that for nearly 10 to 11 hours without charging it. Okay, this is one aspect, but the moment we say that we are speaking about a tablet or a phone or anything like that, or even a laptop, we have a cost that comes with it. So the design goal here is mix of two things. We need the longest battery life, which comes at as less price as possible. Or it can be that our goal is somewhere in the middle ground, wherein we need not uh, expect the highest performance, but rather I expect a above average performance for a lower cost. So the performance cost ratio is the design goal, which is the best trading point. As you have already guessed, we have different products that will dictate what the goals are for that particular products. So I'll present few of the pictures here. Many of them are picked from Google, simple Google search. So here is the PC. At least few years back they were available everywhere. Now only in some your computing labs typically. We have a mouse and a keyboard, and these would be typically the input devices, and the display or the monitor is the output device, and the the black box that is sitting here is the CPU. That's where all the computation happens. The inputs from the keyboard and mouse are connected to the CPU, and it performs something and displays the result on the monitor. A slightly shrinked version of the same is a laptop, wherein instead of a mouse we have a trackpad as an input along with the keyboard, and we have a display attached to it. Now, if you look at the size of the CPU, it has shrunk from this box to a simple, uh, you can say a flat paper type. Obviously, the computing capability of this CPU and the computing capability of this laptop will vary. We can't expect the same intensive computation to be performed in a laptop that we typically do on a PC. Further, if we look at the portability aspect, we have what's called as a tablet, wherein the input is just the screen, touch screen primarily, wherein we type, and the display is still on the same touch screen. And the capability of a tablet are few lesser than the computing capability of a laptop. Further, we have the smartphones, wherein just like the tablet, the input and output are the same screen. And if you want to perform, let's say, a simple matrix multiplication on a laptop and compare it with how the smartphone would perform the same thing, you'll be very surprised on how inefficient your smartphone is. It's not built for that primarily. It is not built to handle computationally intensive applications. Of course, nowadays we do have some heavy graphics driven computer games which run very efficiently on a smartphone than when compared to a laptop also. But then you also have to see how frequently you charge your phone, because the battery capacity of a smartphone and a laptop are quite different. So the first four were wherein where we were looking more at the portability aspects, which was limiting the computational capability of the products. If we move towards more computational capability beyond the PC, we have what's called servers. We have one on the left side here, which is called tower, and here we have two placed on one top of other, which are called rack servers. The computational capability of these servers is much higher than a typical PC or a laptop. Now, you stack up many such rack servers and place them in these cabinets, and if you have a series of such cabinets, that would become your data center or high performance computing center, like the one we have in the department and the institute. Here, if you look at the input and output, all we will be doing is trying to do a remote login and use this primarily for its computational capability, not for an interactive kind of experience. Extending that is what we have as supercomputers. This is Fugaku Japan by Japan. This is one of the fastest super computers at present in the world. This setup is highly optimized for performance when compared to a typical data center. Maybe in the data center, we are more worried about the power consumption and the cooling that needs to be provided to this data center. But when it comes to supercomputer, the only goal that we have in mind is performance. We need the highest performance that is possible, and we are ready to forego the power, the area, or even the noise, etc. All we want is more and more computational capability. Another dimension of computing landscape is what we have here. We have some drones. Now, if you look at the input to the controller in each of these drones, it would be the elevation, the altitude, maybe it's taking some pictures, those would be the input. Maybe you wanted to process something. So those would be the inputs, and maybe some remote based inputs can also be given so that it responds and acts accordingly. And what would be the typical output would be the speed at which each of these rotors will rotate and which direction they have to go, etc. Another popular product is a smart home, primarily driven by uh, a product like an Echo by Amazon. Now, what is the input to this? It's our speech. And what is the output? It will be either the result of a search that we wanted to perform, or maybe it will go and handle some electrical circuitry at the home, like we would say Echo to switch on the fan. So it generates appropriate signals so that the fan turns on. So for each of these products, there are some different goals. That's the reason we need different computing capabilities, which will consider the input that is possible to each of them and the output that we expect from each of them. Here is the bird view of the Google data center in Netherlands. You can see the buildings are huge. In fact, your typical container trucks look like toy trucks here. Now imagine the power supply that needs to be given to such a data center, and try to imagine the amount of heat that is generated from the data center. How do we dissipate that heat? Even when you try to use your laptop for long hours, it's going to heat up. Now imagine some thousands, and thousands is very small, millions of rack servers stacked up on one top of another, performing millions of operations at any given moment, because millions of people across the world use Google for one work or another. Now, how do we handle such huge heat? So, the cooling cost, we need to cool these systems with appropriate cooling mechanisms, right? So, those also need to be considered when we want to build a data center. Okay. Another aspect that I thought you would be finding it interesting is the current discussion about self-driving cars. What we typically expect a self-driving car to do is it will pick inputs from a lot of sensors. It can be a radar or some video at the front or at the back. No, there can be GPS, and there can be a sensor, ultrasonic sensor for distance, etc., tire pressure sensors. All these will be working together and directing the car towards the destination. Now, on a funny note, here we have Mr. Bean trying to drive the car sitting on top of it. You can imagine that he's trying to, you know, emulate the self-driving car. Of course, he himself is driving that, but he wants the overall view of what's going at the back, what's happening at the front, and take appropriate decisions, etc. Of course, the very first thing that comes to our mind is safety. You know, even if he himself is doing that, what happens if he presses the brake suddenly? Where is the safety aspect? That is one of the very important design uh, goals for self-driving cars. Uh, some of you would have already had an opportunity to be part of tinkering lab. You'd already have realized that just based on some ultrasonic sensors, you can make the a robocar move, front, back, side, etc. It can detect a object right in front of it and take an appropriate action. But all is good when it's just a toy. But what if there are humans sitting inside that car? We have to be very careful on the safety aspect of it. Otherwise, people will not buy it. So here is one of the very first designs by Tesla, a self-driving car, and it's demonstrated on road at quite a few places across the world. It still needs to be uh, getting a worldwide appreciation yet, but trial runs are going on. Now, even if we do not consider self-driving car, the cost you put in to buy a car, 40% of it will go to the underlying circuitry. It's not just mechanical devices or mechanical parts. This is for a typical car. Now imagine what would be the demand for computation for a self-driving car, and what is the cost corresponding to that. With all these in mind, what we have at the moment is we have some different types of products, and we have specific goals to each of them. We try to understand what each of them is meant for, how we can use them, what would be the input and output, etc. how will computer architecture help you? Why we should study computer architecture? Will it help in addressing these issues? Yes, it does. It will help us to build better systems. Better systems in the sense which can be faster, or which can be cheaper, which can be smaller in size, and more reliable than they are today. Or it can also help us to enable new applications. For example, a 3D visualization which gives a real life feel, or the previously discussed self-driving cars or driverless cars, or a very important thing that during the COVID times it has even more importance to it, is personalized treatment and personalized medicine. We have almost 7 to 8 billion people now. Each one of them has their own genome, and we need to analyze and give an appropriate medicine which does not have any side effects, etc., etc. Now imagine the computation that is required for it, and imagine what if that computation is not accurate. It can lead to a more severe health scenario for that particular patient. So we need to be extremely careful. We need to cross check whatever we are trying to advise. Also, computer architecture will help us overall to build better solutions. Many of the software innovations that you see today are heavily depending on the architecture that they work on. Like I mentioned, the computer system stack, the top layers are the software. They need to be tightly coupled to the hardware to get the best performance and best price. Or why we need to study computer architecture is to primarily know how computers work the way they work. Okay. At this moment, I also want to take a few moments to give some of the latest things that are happening in computer architecture. The very first product you can say that is Intel's Optane persistent memory. It is primarily based on a non-volatile main memory, which is 3D crosspoint, and it gives huge memory capacity when compared to the typical DRAM based main memory. So here you see a 128 gigabyte device in front of you. Another interesting direction is Cerebras Wafer scale engine. The size of this chip is huge. It has 1.2 trillion transistors, and just for comparison, this is the size of a typical high-end GPU that we have today, the largest GPU in NVIDIA Titan 5, we can say. The Cerebras, if you look at its computational capability, it has nearly 4 lakh cores, and it's primarily targeted as an machine learning accelerator chip. And you are already aware that many of the machine learning and AI algorithms are also using the underlying GPUs. Now, with so many cores embedded, imagine how fast it would be. But if you look at the size, we also need to question on where we can deploy it. Obviously, if we want to deploy it on a mobile platform, it would be more challenging. We also need to consider how much power it consumes to perform an operation. So there are a lot of design aspects that go into the architecture even before we start building one. Another product is UPMEM, wherein instead of getting the data from the main memory to the CPU and back and forth, the architects are exploring the possibility of computing within the memory itself. so that the transfer of data from the CPU to the DRAM is greatly reduced. Now, how does that impact me? What it means is we are going to consume less power to perform the same computation. Also, we are going to get it done faster. So we are going to look at what a DIMM module is, what DRAM is, etc. As we go into the memory module. So here is the self-driving computer chip, or the entire board you can call it, built by Tesla in 2019. Like I said, uh, if you are looking at self-driving cars, safety is of utmost importance. That is the reason we have two chips on the same board. Each of them works in tandem so that they can share the load, and in an eventuality when one of them fails, the other can handle all the tasks. But make sure that the humans sitting in the car are still safe and reach the destination. And each of these chips, if you look at it, are machine learning accelerators. We have 6 billion transistors in each of them, and we are going to look at these G flops, what that means, etc. So we have a GPU along with 12 ARM CPU chips with it. We are going to look at what GPU and CPU are also. Okay, following that, we have another interesting development from Google, which is Tensor Processing Unit. Again, it's primarily built for machine learning and AI algorithms as an accelerator. So here are three generations of TPUs, TPU 1, to 2, and TPU 3. How each varies is we have four TPU chips in TPU 3, version 3 and version 2 when compared to version 1. And if you look at the memory each of them is carrying, so TPU 1 was primarily based on a slower version of memory which is DDR3, but TPU 2 and TPU 3 versions are having high bandwidth memory. TPU 2 has 64 GB of it, and TPU 3 has 128 GB of it. Each of them can handle not only an integer operation but also floating point operations. Then the computational capability of each of them is huge and increasing. We can say scaling from TPU 1 to 2 to 3. And TPU 1 was primarily based for inference, but TPU 2 and 3 were built for both training and inference for many of the machine learning algorithms. Now, if any of you is unaware, in a typical machine learning application, there will be two distinct phases. One is the training, another is inference. During the training phase, we feed it with lot of data so that it trains itself, and during the inference we feed it with the new data so that it, based on its previous learning, it's going to make a decision. For example, if our ML application is identifying cats in an image, during the training phase we are going to feed it with lot of images which can have cats, which do not have cats, which have cat pics in different angles, etc. And during the testing phase we are going to give it a new pic which can or cannot have cat, and we expect the algorithm to identify it accurately. Another interesting landscape is quantum computing, wherein each individual atoms in the states are manipulated to perform some computation. Google and IBM are leading in this effort, but just from the picture you can see that it's not as compact as a typical CPU, and imagine the requirement of the cooling also, it's huge. So it's not mature yet that it can be in the mainstream products, but it has an interesting computing capability or very huge computing capability, much higher than a typical semiconductor based device that we see today. Along with the products and goals and etc., what we have in over the past couple of years is microarchitectural attacks. What does an attack mean? Some aggressor is trying to steal your data at the microarchitecture level. They understand how the underlying hardware works and they want to exploit some of its loopholes. There are many versions of it: Spectre, Meltdown, Zombie Attack, then we have MDS, and then we have CPU fail. All these are very lethal with respect to the data. It's like you're just running your program on your own system without connecting to any internet or anything like that. But some aggressor's program is secretly collecting all your data, and the moment you are connected to any of the networks, it passes over the data. Like I mentioned, many concepts are being investigated today, and the very nature of the computer architecture landscape is that it changes very rapidly. What the design was in the chip yesterday need not be relevant today because it's completely driven by the applications that they need to handle and the demand from the users. So, till 3 or 4 years back, security of the data was not a big issue. And like I mentioned in the previous slide, now the security vulnerabilities have shown up that we need to build our chips in a more secure fashion. So our design choices have a new element in them, which is security. If you look at the major problems that we have today, we have applications which have huge hunger for data. There are severe power and thermal constraints that in the products that we build today. If you look at the complexity of the design, it's increasing day by day. And then we have difficulties with technology scaling. Right now we are at 7 nanometer, but scaling further to uh, to a lower device lengths is getting more and more difficult. Then we have memory bottleneck because the memory is not as fast as your computing a CPU or a GPU or a TPU. Then we have the reliability. Following that, we do have the security and privacy issues. To answer them, some new computing paradigms have been proposed. Some of them we have already touched, like processing in memory. Then there is a neuromorphic computing, wherein the very nature of human brain is being studied and replicated in the hardware. And like I mentioned, there is quantum computing. There are more and more accelerators which are primarily targeting one or a set of applications of similar nature. Here we are flooded with applications from machine learning and AI at the moment. Then we have graph analytics, then genome analysis. Following that, we have a few systolic architectures which are quite orthogonal to the traditional architectures. TPU is an example. Then we have a lot of new memories that are being explored today. And the secure hardware is one of the hot topic. Now we do have many interesting things that come up, and there are many new challenges and opportunities. And what does this course help in is to understand the basics of such computing systems. Now I would like to touch on the very specific role of the computer architect. What is the role of a computer architect? So here we have Professor Yale Pat from UT Austin. He's a very influential person in the computer architecture field. He has defined that an architect should look backward, forward, up, and down in all the directions to make a well-informed design choice. Now, what does it mean? What do we mean by looking backward? We have to understand the previous designs, how some particular chip was designed, what were the limitations on it, what were the limiting factors. At the same time, we also need to understand what are its capabilities and what it was meant for, means the past applications or also called workloads. This will help, this overall analysis of what was there previously will help us to understand what needs to be done next. Looking forward into the future, basically looking up into the future means imagine or try to imagine what all applications or programs that users will be running, let's say 5 or 10 years down the lane, or even we can say 50 years down the lane. Now, what is the computing capability requirement for such applications? So our current day hardware needs to be tailored towards those applications. Be a dreamer. Study the future requirements so that it will help us to tailor make the hardware. Push the state of the art. State of the art, the term means anything that is the latest in the current field. Either can be a product or a technique, a design choice, etc. Look upward means looking up towards the up in the computing stack where we have all the software layers. It means basically looking at the real life problems, their nature, that would be the application framework, and try to come up with better algorithms and develop architectures for those refined algorithms to solve these important real life problems. Look down means look down in the computer system stack and find out what is the limiting factor at the device and circuit level, or even at the maybe come up with a new physics also. Understand the capabilities and limitations of the underlying technology and build the future technology. Now, if we look at the role of an architect, we need to have the maybe may not be the exhaustive knowledge of the software stack, but a decent knowledge. We need to have a decent knowledge of the hardware layers in the stack so that we can build better computing systems. For example, if our application is a self-driving car, now we need to analyze what are all the inputs that it need, what is the reaction time that it demands, what are all the design choices that we need to imbibe, and accordingly we build an algorithm primarily based on machine learning or AI, etc. And we try to run on a hardware. At present we have Cerebras, TPU, etc. This is the role of a computer architect. Understand what happened before, what needs to be done next, what are the current applications demands, what are the limitations of the hardware, and considering all these parameters, come up with some new designs. So computer architecture has inputs from the technology, inputs from the applications, input from the programming languages, inputs from the operating systems, and also the ingenuity of the architect, that is you. You're all computer architects or would be computer architects, and your own ideas can change the direction in which a particular design choice is going. If you are curious to know what is the future of computer architecture, here is a very interesting talk by two people. They are Turing Award winners in 2018, John Hennessy and David Patterson. They are very influential in the field of computer science, sorry. And they are one of the pioneers who have built and prophesized many of the computing uh, platforms that we have today. And they delivered a Turing Award lecture titled A New Golden Age for Computer Architecture, domain specific hardware software co-design, enhanced security, open instruction sets, and agile chip development. If you're interested, I've provided the link here. Go and go through it. It's really interesting and very insightful on what are the current demands on the hardware. By the way, if you haven't already realized, Hennessy and Patterson are the authors of the textbook that we are following for this course. Along with the lecture, I also suggest you to think about the societal grand challenges that were proposed by National Academy of Engineering, and the most updated list was released in 2018, where they have added two more fields, which are universal communication and build flexible general purpose AI systems. Now, AI systems means not specifically not only the algorithms, it's the entire system. Here, the role of an architect is very crucial because he can do wonders by building a very efficient system for an AI application. So, Internet for all. Here we have enabled universal communication. Then I already touched upon AI systems. We have another societal challenge, which is reverse engineer the brain, basically the neuromorphic computing aspects, one part of it at least. Then secure cyberspace. Then we have advanced health informatics like the genome analysis, etc. Then we have enhanced virtual reality. This is an application and we can tailor make a hardware for it. And then we have the most relevant aspect, which is advance the personalized learning, even if it is in a remote fashion with the way currently we are going. And here we have engineer better medicines with more and more analysis. So all these need one form of computing or another, and as computer architects, it's our duty or it's our primary job to understand what they demand and how to build the hardware for it. So with all these points, I welcome you all to the course. It's a very interesting course, which, like I mentioned, touches upon many different aspects across the computer system stack, and you will see the relevancy of it more and more as we go through the course. With that, I'll pause this lecture. Thank you.